Hi everyone, can everyone see my screen?
Yes.
All right, great. Good morning, everyone. My name is Shourav Rabbani, and today I will present my thesis. Before we start, I extend my sincere gratitude to all the committee members for their time and guidance. In addition, I am grateful to the NIH for their sponsorship that partly supported this work. Let's begin. Here is the outline of this presentation. We'll start with the introduction and background review. We'll summarize them into our problem statement, formulate research objectives, present the results for each objective, and do the conclusions. Tabular data are at the heart of many application domains. For example, finance, healthcare, recommendation systems, cybersecurity, anomaly detection, customer churn, and many more. However, deep learning is not good on tabular data. We know deep learning is great on image and language data, but this is not the case here. This tells us that tabular data is different. How? One, they are composed of heterogeneous features. And two, unlike images or language data, positions do not matter. In short, there is a permutation invariance. Let's see some examples. Consider this tabular data with three features: age, education, and wage. All these features tell different things about this sample. If we swap the feature positions, we know that this sample is still the same. So feature positions do not matter. In contrast to images, the pixel intensity, and they're arranged in a manner that makes us see a turtle. If we were to swap out the pixels, we can no longer see a turtle, and so feature positions do matter. Such differences in data and shortcomings of deep learning in tabular data is clear in the literature. For example, Caldera et al. Say deep tabular data is the last unconquered castle for deep learning. Shourav et al. Say deep learning is not all you need. Therefore, improving deep learning on tabular data is a hot research topic. These shortcomings may be because of some assumptions of tabular data. First, samples are assumed independent and identically distributed. And second, there is no feature interdependency. Let us see with an example. Suppose we have two samples. IID means sample 1 cannot give any information about sample 2. Any feature here is not dependent on the other feature. If we relax these assumptions, it may help tabular data learning. We find that attention-based methods show promise on tabular data. However, they're only tested on a few data sets and only done with supervised learning. Let us first see how attention mechanisms work, and then we'll discuss the limitations of supervised learning. So attention is not a new concept. It was popularized by the transformer architecture by Vaswani et al. And revolutionized the natural language processing field. What is attention? It is basically a mechanism that learns dependency between words. Consider a sentence: how are glacier caves formed? The heat map shows attention scores between each word. Deeper shades of blue means more attention score. In the case of an NLP model, we're trying to learn the representation of the word how. The model knows it is dependent on the word formed. Similarly, caves and glaciers. Attention provides a faster way to compute dependency than existing models like recurrent neural networks. And these computations can be parallelized. So let's see how attention works. So attention between feature, we have our sentence, how are glacier caves formed? We create initial representations using a process called word embeddings. We get a matrix like this where each row corresponds to the A word. To compute attention, we need to compute three matrices: query matrix Q, key matrix K, and value matrix V. These three matrices are used to compute attention scores and improve the representation using equation. This part tells us about the attention scores, which are used to combine the representation, that is, attention between features, and output new representations. But how can we use it for tabular data? Simple. Replace the input and create representations of the features also. Everything else is the same. Moving forward, we'll represent this part as attention QKV. Now let's see how we can attend between samples. Consider we have 3 samples. We create feature embeddings for each of these. And we reshape them such that each row now corresponds to a sample's embedding. Now we can use the attention module from last slide to leverage information between samples. We'll refer to this as attention between samples in the next slides. Now let's put them all together and see how we can use it for supervised learning. Before we start, I'd like to say for classification or any task, we have to add another feature called the CLS token. We want to use this feature and let it get shaped by the attention mechanism. So first, we let it get shaped by between feature attention, and then we allow it to get shaped by the between sample attention. Finally, we take all the CLS tokens and pass it through our MLP classifier to get prediction logics. From here, we can just compute the loss, and then we can backpropagate all the gradients for learning purposes. Okay, but are there any other way to leverage between sample relationships? From our literature search, we note that there is another way, and that is graph neural networks. Consider graph data, that is a collection of nodes and edges. Here, a graph is a node of has 4 nodes and some edges that connect it. Graph neural networks leverage information from all connecting nodes to generate representations. So we can see they do not have the IID assumption as tabular data. That's great, but how can we use it for tabular data? We'll visit it later, but let's move on. From literature, we note most deep learning is done using supervised learning. That is, they use labeled data. But there are limitations in using supervised learning because real-life data is mostly unlabeled. That is because annotating tabular data is time-consuming, tedious, and hard. Consider images where we can simply look and tell apart 2 classes. Tabular data is not so easy. This leads to inter-rater variability, and most of the labeled samples may not be correct. In addition, they're prone to overfitting, and minor changes are susceptible to minor changes can change the outcome. So we note we have to avoid these limitations, and unsupervised learning may help. So clustering is the most popular form of unsupervised learning. However, traditional clustering has some limitations. As the number of features increase, they're not scalable anymore. We then have to use dimension reduction techniques like PCA, but they create representations that do not align with clustering objectives. So we need to address these limitations, and deep clustering is the answer. It can cluster on high dimensional data and can produce cluster-friendly representations. To understand the landscape of deep clustering, we use a survey paper written by Zhu et al. That provides excellent review of the literature. We summarize the important parts. There are 2 key modules, 1 for representation learning and 2 for clustering. Each of these modules have different methods and have multiple ways to combine them. Let's explore them briefly. Zhu et al. Found several methods in the literature that is used for representation learning and clustering. In representation learning, we have autoencoder, generative, contrastive, mutual information maximization. For clustering, we have relation matching, pseudo-labeling, mutual information maximization, contrastive, self-training. Similar names in these two modules are basically a package deal. They cannot be mixed with other methods. For example, mutual information maximization. However, for our purpose, we will be focusing on autoencoder based because we want to compress high dimensional features, and self-training because we want to preserve clustering quality. Other methods do not focus on this, but before we move forward, let us note that attention-based representation learning was not used for clustering. In 4 different ways. One, multi-stage, where each module is trained in a sequential manner. Iterative is the same as multi-stage, but they are done in smaller steps and iteratively. Generative combines all these two together and is trained and is very integrated. And finally, we have simultaneous learning where each module is trained together. For our case, with autoencoders and self-training, multi-stage and simultaneously training applies. However, we will be focusing on simultaneously training because this is the state of the art and it solves some of the problems of multi-stage training. We'll explore them soon. Before we move ahead, let us quickly review autoencoders. Given an input with large features X, we want to compress them into low-dimensional representation Z, such that we can construct them back. For that, we use a neural network with a bottleneck, and we train the network to minimize the reconstruction loss. Next, we want our clustering module to produce good clustering. For that, we optimize the network with KLD divergence loss. Here, P is the target cluster distribution, what we want, and Q is the cluster distribution from our network. That is, we want to make these two distributions as similar as possible. This method was used by Jia et al. In their paper called Deep Embedding Clustering. Now let's put them together in simultaneous learning. This is the most active direction in deep clustering for our line of work. It solves some of the problems of multi-stage as shown by Gu et al. In their paper called Improved Deep Embedding Clustering. So what are these methods? Let's explore them. Deep embedding clustering uses multi-stage learning. They pre-train a denoising autoencoder. Afterwards, they remove the decoder and then compute cluster assignments from the embeddings using T-distribution kernel. They compute the P from Q and then fine-tuning the new network using KLD. But there is a problem. In fine-tuning with only KLD loss, it has removed local structure property. Basically means the representation quality has become poor and we can no longer reconstruct the original features. The solution is simple. We can fine-tune the both modules together. And then we use a combined learning objective. Notice we have a gamma parameter. This is used to balance the two losses. We identify some limitations of existing methods. One, clustering assignments are done using T-distributions. Authors of DEC based this on the seminal Tisney paper by Madden and Hinton. The paper was done for visualizations in 2D, whereas clustering is done on higher dimensions. So they're not the same. And two, these methods are only tested on image datasets. On tabular dataset, the representation learning may not be optimal or clustering friendly. We look into literature to explore their effectiveness on tabular data. We find results from Abraham et al., who are the first to explore the effectiveness of deep clustering methods on tabular data. Different results are shown in rows and methods in columns. First, these two are our traditional methods. These are the methods we have explored, and these are the other methods that are based on autoencoders and KLD. So let us focus on traditional IDEC. From that, we observe traditional methods are still competitive. Deep methods designed for images are not optimal. Therefore, deep methods should be customized for tabular data. However, IDEC shows promise, so there is room for improvement. Let us recall limitations from earlier slides and create our problem statement. IIT assumption on sample and feature independence may limit representation learning. We see improvements when these are relaxed in attention-based learning. However, they are not fully tested on many tabular datasets. Deep learning is mostly supervised and it has limitations. Existing deep clustering methods are designed for images and not great on tabular data. Finally, we find that attention-based representation learning is used for classification, but not clustering. So in this thesis, we carry out two research objectives to address the problem statement. First, we investigate the between sample and between feature relationships thoroughly for tabular data classification. And second, we take the strengths of attention-based learning for deep clustering. That is, we propose an attention-based clustering of tabular data. So let us discuss the results on two objectives. For the first objective, we have made progress. Here we have a list of methods. We have traditional methods like logistic regression, gradient boosting trees, and our basic neural networks like MLP. Advanced deep learning methods like attention that leverage between feature and sample attention. And lastly, graph-based neural networks that can leverage between sample relationships. But remember that tabular data are not graphs, and we cannot use them outright. So we address them first. For that, we propose a method to model tabular data as graphs. Given a tabular data, we compute similarity between all sample pairs. We then set a similarity below some threshold. In this example, we set it at 0.7, and anything below are set to 0. And then we can use this matrix for adjacency and create our graphs. For our unweighted graph, we can replace on non-zero with 1 and create an unweighted graph. This threshold here is a hyperparameter, and we use a validation set to get the best hyperparameter. For our model evaluation, we use a 10-fold cross-validation scheme. Here, 70% of the data is used for training. We use the 20% for best hyperparameters and early stopping, and finally, we test on the 10% left out dataset. We do this for 10 times, and then we get the average. Here are the results of the dataset from UCI data repository. We present them as ranks where lower means better. Let's highlight the top methods for each dataset. We see that some methods perform on par with traditional or basic neural networks on some datasets, for example, breast cancer and dermatology. However, the deep learning are very good when they leverage the between sample and between feature relationships and come on top on some datasets like mice, Parkinson's, satellite, synthetic, vehicle. Overall, in this objective, we have leverage between feature and between sample relationships. This beats traditional models on 5 out of 10 datasets and draws on 2 datasets. This shows the effectiveness of between feature and between sample relationships. Moving forward, for objective 2, we propose an attention-based clustering. First, we use attention-based learning. We have the CLS token, and we let it get shaped by the different attention models. We take the CLS token, and instead of classification, we predict the clusters from it. Here, Q is the cluster probabilities. And using all the feature embeddings, we reconstruct the features to let it work like an autoencoder. That is, our objective is we will do a reconstruction loss and a KLT loss. Remember, we have a gamma parameter to balance them. We select 16 different tabular datasets taken from OpenML classification benchmark suite. We select a mix of hard and easy. We compare the performance of a linear classifier and a nonlinear classifier like GPT, gradient boosting trees on each dataset. If gradient boosting trees are better than cheap logistic regression by 5% or more, we classify them as hard. Otherwise, they are classified as easy. This allows us to test our method on tabular datasets of different domains and difficulty. Since clustering does not involve labels during training, overfitting does not apply. So we use 100% of the training data for our experiment, just like DEC and IDEC method. First, we pre-train an autoencoder and then use our joint training for the clustering methods. Finally, we compute the clustering accuracy. We run these experiments for all datasets and compare the performance and rank. Our preliminary results show pre-training may not be necessary. Recall that the first 8 are easy and the last 8 are hard, and we have 3 types of attention. A self-attention or between feature that is call, between sample attention that we call it as row, and both of them together in sequence, we call it call and row. Overall, rank shows that without pre-training is better than with pre-training. And within them, we find that self-attention or column attention is much better. So we use them for our proposed method. So we put them together, we have a self-attention, and we borrow the clustering from IDEC method. And these are the results from our benchmark. We see that on 3 and traditional works on 6 data sets. We can use the overall rank to compare them. But we must note that some of the data sets here where our methods did not go well, we do not recommend them for deep clustering. Instead, you should use tabular data and traditional clustering, and this causes our rank to go down. Despite that, we note that our proposed method is better on hard data sets than easy data sets, where traditional methods suffer. And we note that adding attention takes IDEC from rank 4.3 to rank 3.3. That is as close as our traditional methods. So in this objective, we have proposed a novel deep clustering method that leverages between feature and sample relationship. Our results indicate that between feature relationship is better for clustering. It beats the traditional models on 2 easy and 5 hard datasets. Overall, our proposed method is better on hard datasets. And our rank shows that adding attention elevates deep learning to near traditional clustering. Before we move on, we'd like to address some concern. You may be wondering why between feature attention is done before between sample attention. We'd like to thank Dr. E for raising this question. In response to that, we designed a small experiment. We will use different attentions here. For example, we can replace this part with between feature attention or between sample attention, or them in sequence, or take the reverse, or do them in parallel. We test them on a 5-fold cross-validation scheme. Remember there are 5 different attentions now, and we note that all different attentions are useful, but on average, we see that self-attention here is the worst. That is followed by between sample. But if we do them in sequence, we have the best rank. And this is not the same if we reverse the sequence and even do them parallelly. This tells us that while self-attention is not the best, it is an important requirement for better representation learning. In conclusion, our thesis aims to improve deep learning of tabular data. It challenges IIT assumption and relaxes them using attention-based learning. This allows us to leverage between feature and between sample relationships. And experiments reveal attention-based learning shows promise on tabular data. But more improvement is needed to overtake traditional methods. Future work will try to focus on cluster distribution itself, and other works should identify and challenge other assumptions of tabular data. In doing this thesis, Objective 1 has resulted in 2 publications. We have one conference publication in 19th International Conference on Data Science in Las Vegas. We have another journal paper that is under review. Objective 2 should result in another publication. We plan to complete and submit by the end of spring 2024. These are some of the references used for these slides. Thank you again for joining my thesis presentation. I welcome everyone to read my thesis for more details. If you have questions, I will take them now.